Okay, it's time. I think we can start now. Mm, okay, good morning. Welcome back to morning session at the third day of APCTP Focus program. And next speaker is Edward Witten from IAS, and he will give us talk about an algebra of observables for digital space. And would you please start?
Oh, well, thank you very much for the introduction and for the invitation to give this talk. So I'll mainly be talking about a recent paper that has the same title as the talk, with Chandrasekhar and Pennington and Longo. And to some extent, but I won't have much time for it, there's an earlier paper that I wrote last December. Something I want to mention is that the inspiration for this work came from two papers by Liu and Leutheiser. I know that Liu gave two talks the other day at this conference. Perhaps he talked about this work. Unfortunately, I wasn't able to attend those talks. I'm going to begin by just reviewing a couple important ideas at the beginning of black hole thermodynamics. The idea that the entropy of a black hole should be understood as entanglement entropy goes back to Raphael Sorkin in 1953. The basic idea was the following. In a quantum field theory, divide space into two regions, A and B. Sorkin had in mind that B was the interior of the black hole behind the horizon, and A is the region outside the horizon. But for some general remarks, it doesn't matter what A and B are. Let psi be a state of the system, and let rho sub A be the reduced density matrix of the state psi for measurements in region A. It turns out, as we'll discuss later, that's a problematical concept. But naively, you can hope that if you're only going to make measurements in region A, you're dealing with a subsystem of the bigger system, and it would be described by a density matrix. So let rho A be that density matrix. And then one can define its von Neumann entropy, S, which is minus the trace of rho A log rho A. So Sorkin's idea was roughly that this would be the Bekenstein-Hawking entropy of the black hole for the case where B is the region behind the horizon and A is the region outside the horizon. When he calculated, he found that this quantity is ultraviolet divergence. And the divergence is actually independent of the state psi. The coefficient of the leading divergence is proportional to the area A of the boundary between the regions A and B. So Sorkin had gotten an entropy that was proportional to the area. The only problem was that the coefficient was infinity. For the Bekenstein-Hawking entropy, the coefficient of the area is not infinity, but 1 over 4g. However, Sorkin's intuitive idea was that he had done the calculation ignoring gravity, which was like setting g to 0. And infinity is the correct answer if you try to set g equals 0, assuming that the general formula is that of Bekenstein and Hawking. So Sorkin's hope, in modern language, was that gravity would somehow cut off the divergence, and instead of getting the area times infinity, you get the area times 1 over 4g. I'll jump ahead another decade to Susskind and Uglum, who advanced the subject with a very simple observation. Bekenstein had defined the generalized entropy in the presence of a black hole as the area over 4g, except here I'm going to be more detailed and include the 1 over h bar in the formula. So it was really the area over 4g h bar, plus what Bekenstein called S out, the entropy of ordinary matter and radiation outside the black hole. And Bekenstein assumed that thermodynamics was applicable for the outside matter and radiation. Of course, thermodynamics isn't always applicable. It's only applicable close enough to thermal equilibrium. So this wasn't meant to be a universal formula. But Susskind and Uglum said that if we interpret S out as the von Neumann entropy of the density matrix of the region outside the horizon, then suddenly it does become a more universal formula, because that version of S out is always defined, And they discovered an amazing fact, which is that the generalized entropy is better defined than either term is separately. So S out is not well defined because it has an ultraviolet divergence, first explored by Sorkin. But the area over 4G has a similar problem because there's an ultraviolet divergence in the relation between the bare Newton constant and the physical observed Newton constant G. So the relation between G naught and G is like this in one loop order. Now, when Hawking had derived the Bekenstein-Hawking entropy, Hawking had not taken into account loops that were normalized in Newton's constant. So Hawking's answer was really, Hawking didn't write it like this, but a more precise way to write Hawking's answer was that Hawking's answer was the area over 4G naught H bar. But 1 over G naught is ultraviolet divergent, because if you express it in terms of the physical 1 over G, if we try to explain what's the entropy of the universe in the presence of a black hole, presumably then by G we mean the physical observed Newton's constant. What else could we mean since we don't know what G naught was? And that's formalism dependent. So Hawking used G naught, but we won't interpret the formula in terms of G, and there's an ultraviolet divergence in the relationship between them. And Susskind and Oakland argued that the ultraviolet divergences in S out cancel those in 1 over G. So the generalized entropy is better defined than either of the two terms on the right-hand side of the formula. Now, at this level, we could be talking about either a black hole horizon or a cosmological horizon. In this talk, I'm going to give a slightly abstract explanation of why it is that entropy is better defined when gravity is included, at least for the black hole and de Sitter space. De Sitter space is the sort of prototype of the spacetime that has a cosmological horizon. So, well, how are we going to understand why gravity makes entropy better defined? Gravity makes entropy better defined because the purely quantum field theory entropy of the outside region is ultraviolet divergent. Gravity tells us to add something which miraculously cancels the ultraviolet divergence, giving a well-defined expression. So we're going to have a slightly abstract explanation that, at least to some extent, explains why gravity makes the entropy better defined. First of all, in ordinary quantum mechanics, when we consider the entanglement between two systems A and B, usually we assume at the start that each system has its own Hilbert space, HA or HB. The combined system then has a tensor product Hilbert space, HA tensor HB. A state psi AB in this combined Hilbert space might be a simple tensor product of states psi A and psi B of systems A and B. In that case, systems A and B can separately be described by pure states, namely psi A and psi B, and there's no entanglement entropy. But a more general state is not a simple tensor product. It's a linear combination of such things. In that more general case, we say that the systems A and B are entangled, and then system A or B has a non-zero von Neumann entropy. The point is that in ordinary quantum mechanics, whether or not a system has a non-zero entanglement and entanglement entropy is a property of the state. It's not a property of the system, it's a property of the state. That's not so for entanglement entropy between different regions in quantum field theory. As I explained when I discussed Sorkin's idea, the divergence in the entanglement entropy found by Sorkin was an ultraviolet divergence. so it does not depend on the state. Every state looks like the vacuum at short distances, and therefore the leading ultraviolet divergence in the entanglement entropy is completely independent of the state. So, unlike the situation in ordinary quantum mechanics, where it's possible to have an unentangled state with zero entropy, here that's not possible. The root of the problem is that it's not true in ordinary quantum field theory that there are separate Hilbert spaces, HA and HB, for the inside and outside regions. There's only a combined Hilbert space H for the whole system. What the separate regions A and B have are not Hilbert spaces HA and HB, but only algebras of observables, curly A and curly B. These algebras act on the Hilbert space of the combined system, so we can view them as von Neumann algebras. A von Neumann algebra is just a fancy name for an algebra of operators on a Hilbert space that's closed under a certain type of limiting operation.
I have a question.
Yes.
So here, if you think this gravitational system, you can think of some non-local observable, some non-local operator. So in that case, how can you divide like an observable A, or like when you say observable, is it like something like a local?
Well, I didn't claim that all operators can be divided. So you've given an example of an operator that can't be divided. What I said is much weaker. I only said that there are some operators localized in region A. Likewise, there are some operators localized in region B. To make an operator localized in region B, roughly, you integrate over B dx with some weight function and then some local operator. That'll give a what's called a densely defined operator that's localized to region B. To get a von Neumann algebra, you want a bounded operator. So for example, you could exponentiate this with a factor of I, which makes it bounded. So that's an example of an operator localized in region B, and there are others. I did not claim that every operator is so localized, or that every operator is a product of an operator in region A or in region B. Your question seems to be aimed at giving one explanation of why that statement is not true. Is that responsive to your question?
Yeah, but I'm like asking like some whether when you say observable, like you can think of the like for example in the gauge theory, you can think of the Wilson line from Wilson loop, so which cover the A and B, but you don't include such kind of operator.
Well, I did not claim that every operator is in HA or HB. So HA would contain Wilson loops in region A. HB would contain Wilson loops in region B. And a Wilson loop that's partly in A and partly in B is in neither algebra. Is that clear now?
Okay, yeah.
There's no claim that every operator is in one algebra or the other, or even that every operator can be expressed in terms of operators in one or the other, not in any simple way anyway.
I see. Okay, thank you.
So, however, what each region does have is a von Neumann algebra of operators that act on the Hilbert space. So we will want to know just a little bit about von Neumann algebras. There are three types of von Neumann algebra. Type 1 is the algebra that you all know about without giving it that name. It's the algebra of all operators on the Hilbert space. So in ordinary quantum mechanics, when we discuss the system A, it has a Hilbert space HA, and the algebra of observables of the system is the algebra of all operators on HA. So in ordinary quantum mechanics, we associate a type 1 algebra to any system. So if a system has a type 1 algebra A, then it can have quantum mechanical pure states, namely states on in the Hilbert space on which A acts. It can also have density matrices and entropies. but it can have pure states, states of zero entropy. The other types of binomial algebra are less familiar. But first, let me tell you about the properties. A type 2 algebra does not have pure states, but it does have density matrices and entropies. A type 3 algebra is the worst type. A system whose observables are of type 3 does not have pure states and also does not have density matrices or entropies. So by now you might anticipate the bad news. In quantum field theory, the algebra of observables of a region of spacetime is always of type 3. This result goes back to Araki in the 1960s. Well, 1965 plus or minus 1. I don't quite remember the year. So to a region in quantum field theory, you can never associate a pure state or a density matrix or entropy. The algebra is of type 3, and type 3 algebras do not have pure states, density matrices, or entropies. The type 3 nature of the algebra can be viewed as the reason that there's a universal ultraviolet divergence of the entanglement entropy. However, it turns out that including gravity in a semi-classical way, which means even in the limit of weak coupling, changes the picture. At least in the case of the black hole or de Sitter space, including gravity at a semi-classical level changes the algebra of the region outside the horizon from type 3 to type 2. So when gravity is turned on semi-classically, the region outside the black hole or de Sitter horizon is described by an algebra in which entropy is well defined, though there is no notion of a quantum mechanical microstate. So we don't solve the black hole information problem, for which you should get an algebra of type 1 that would have pure states of the black hole, but we do get an algebra of type 2 explaining why entropy is well defined, or giving an abstract perspective on why entropy is well defined. Well, in more detail, there are a couple of different types of type 2 algebras. We get what's called a type 2-1 algebra for the de Sitter space and a type 2 infinity algebra for the black hole. These are actually the most important type 2 algebras, are the ones that we get for de Sitter space and the black hole. So since this will be the basis for my somewhat abstract explanation of why entropy is better defined in the presence of gravity, I want to tell you a little bit about what type 2 algebras are. First of all, a type 2-1 algebra is most simply described as the algebra that acts on an infinite collection of qubits in an almost maximally entangled state. Start with a finite system A of n qubits, maximally entangled with a second identical system B, also consisting of n qubits. And I assume that the ith qubit of system A is completely entangled with the ith qubit of system B. For example, in the state that I've introduced here, which needs a factor of 1 over root 2 to normalize it. So with n of them, I put 1 over 2 to the n over 2 outside. So this is a normalized state in which the nth qubit, the little nth qubit of system A, is completely entangled with the little nth qubit of system B. Let A and A prime be operators that only act on the first k spins or qubits of system A, where k is no bigger than n. And define a function f of A, which is the expectation value of A in the state psi. Well, since the density matrix of system A, A was maximally mixed because it was completely entangled with B. So its density matrix is 2 to the minus n times the identity. So f of A is the trace of A times the density matrix, where the trace is taken in the Hilbert space of system A. That's equal to 2 to the minus n times the trace of little a in that Hilbert space. It follows then that f of a prime equals f of a prime a, because each of them is 2 to the minus n times the trace of a prime. Another fact is that f of 1 is 1. To compute f of 1 is 1 because the state was normalized. Or equivalently, because the density matrix has trace 1. So if I set a equals 1, I get 1. The function f of a has a thermodynamic limit in the limit that the number n of qubits goes to infinity, because it's unchanged if we add more maximally entangled qubits to the system, with the given operator a not acting on the added qubits. So for n to infinity, the function f of a can be defined for any operator little a that acts on any finite system, any finite set of qubits in system A. And of course, in the limit of the infinite system, it still satisfies these two relations that we had. They were true for any finite n's, or they're true in the limit. So far, we've defined the function f in the whole algebra A naught of all operators that act on only finitely many qubits in system A. By taking the closure of A naught in von Neumann sense, which means that we allow some operators that can act on any number k of qubits, but their matrix elements decay rapidly when k increases. Anyway, by taking a completion of A naught, we complete A naught to a von Neumann algebra A. It still has a function f of a that has these same two properties. Since f of a prime equals f of a prime a, this function is usually called a trace. But it's not the trace of the operator a in any Hilbert space representation of the algebra. It's more like a renormalized trace in which we removed an infinite factor 2 to the n, or n was going to infinity. The renormalized trace has the property that the trace of 1 is 1. That was true for every finite n, and therefore it's true in the limit. Now, you all know a more elementary, so what I've described here is the Murray-von Neumann algebra of type 2-1. We'll know a more elementary example of an infinite dimensional algebra with a trace. The type 1 algebra B of all operators on an infinite dimensional Hilbert space H. In this example, you can define a trace on elements of B, but it's not defined for all elements of B, only for those that are trace class. For example, the identity element does not have a trace, unless you want to say that its trace is infinity. It doesn't have a complex valued trace. By contrast, from the infinite system of qubits, we constructed an algebra, curly A, in which every element has a trace.
So here, I have a question. Here, you trace of the identity operator is infinity because you remove this factor e to the minus the n, right?
The factor e to the 2 to the plus n. We took the trace at finite n multiplied by 2 to the minus n and then took the limit.
Mm-hmm.
So we multiplied by 2 to the minus n before taking the limit n went to infinity.
Mm-hmm.
The result of that is that the trace function is well defined. Mm-hmm. And it satisfies the key properties.
Okay.
But it's not the trace in any Hilbert space representation. It's a trace in a more abstract sense.
Mm-hmm. Okay.
And it's defined for all elements of the algebra. In the type 1 case, the natural trace of the identity is infinity. And if you try to divide by that infinity, then all the operators that had finite traces would go to trace 0. So The algebra A was an essentially new type of algebra. It's the simplest example of a type 2 algebra. It's said to be of type 2-1. And it was defined in much the way I told you by Murray and von Neumann. Now, if A is the type 2-1 algebra that we constructed and B is the type 1 algebra of all operators on an infinite dimensional Hilbert space, then we can make a third type of algebra by simply taking their tensor products. We let C be A tensor B. That new algebra still has a trace because each factor does, but it's not defined for all elements because of the factor B. In fact, C is a new kind of algebra, said to be of type 2 infinity. It turns out that C is related to the black hole and A is related to de Sitter space. Purely mathematically, these are the most important type 2 algebras. The other ones have more exotic properties. To construct an algebra of type 3, well, I won't use any algebras of type 3 in the lecture, but I told you that in quantum field theory, the algebra of a region is of type 3. So I just want to take a moment to tell you how to make concretely an algebra of type 3. You do the same thing, but starting with the A and B systems being fully but not maximally entangled. By fully entangled, I mean that the density matrix is invertible, but it's not a multiple of the identity. So for example, you could put each pair of qubits in this state, which has a density matrix that has no zero eigenvalues. The density matrix is invertible, but the density matrix is not a multiple of the identity. You can still define the function f of A, which is the expectation value of A in the state psi. And as before, it has a thermodynamic limit. The important difference is that f of A prime is not equal to f of A prime A. So if you take the large n limit of this state and consider operators that act on it in a natural sense, you can construct a type 3 algebra. I won't go through the details, but there's a natural construction starting with this state of an algebra that's a lot like the type 2 algebra, except that because of f of A prime not being f of A prime A, there's no trace, and in fact, you get an algebra of type 3. This is the simplest construction of a type 3 algebra, introduced in the 60s by Powers and then generalized by Araki and Wood. As I think I already said, perhaps, but anyway, algebras of type 2 or type 3 do not have an irreducible representation in the Hilbert space. Oh, I didn't quite say it in those words. Whenever such an algebra acts on a Hilbert space H, it always commutes with another algebra of the same type, either type 2 or type 3, as the case may be. For example, we constructed our type 2 and type 3 algebras as algebras of operators on the A part of a bipartite system AB. So in that construction, they commute with an identical algebra that acts on system B. There are other possible constructions, but whenever you have a type 2 or type 3 algebra that acts in a Hilbert space, it will commute with another type 2 or type 3 algebra, another algebra of the same type. Now, as I've said a couple of times, the difference between a type 2 algebra and a type 3 algebra is that a type 2 algebra has a trace and a type 3 algebra does not. Moreover, in a type 2 algebra, the trace is non-degenerate in the sense that if f of A is any linear function on an element A of the algebra, any complex valued linear function, then f of A is equal to the trace of A prime for some unique A prime in the algebra. In particular, if A acts on a Hilbert space curly H, and psi is a state in H, we can consider the linear function that takes A to its expectation value in the state psi. Using this property of any linear function, we discover that this linear function is the trace of rho times A for some rho in the algebra, which I call the density matrix. And I call it the density matrix because it satisfies what in ordinary quantum mechanics is the defining property of a density matrix. So we've learned that a state of a type 2 algebra has a density matrix. Any questions on what I've said?
Hi, I have one question. I think so far you consider type 1, type 2, type 3 from the algebra, and you only consider the bounded operator. But in a theory, we have the bounded and the unbounded operators. So how do you expect that we can just consider bounded operator, then I can classify the types of entropy?
Well, first of all, unbounded operators don't form an algebra because you can't multiply unbounded operators except in special cases. Yeah. So if you want to make an algebra, you have to consider bounded operators. Yes. If you have any possibly unbounded operator,
yes,
and any bounded function of phi is a bounded operator. So whatever are your favorite unbounded operators, you consider arbitrary bounded functions of phi. And by considering bounded functions of phi, you can extract the same information that you would have had by considering phi. Technically, it's advantageous because bounded operators form an algebra. For example, you might have, if phi is self-adjoint, you could have measured it. But that would have been equivalent to measuring bounded functions of phi. Is that okay?
Yeah, thank you. It's good. Yeah.
Okay, sure. Any other questions? Once we have density matrices, we can also define entropies. So a state of a type 2 algebra has an entropy. However, in physical terms, the entropy of a state of a type 2 algebra is a sort of renormalized entropy from which an infinite constant has been subtracted. For example, let's go back to the system A of n qubits maximally entangled with another subsystem B. The A system has entropy n, infinite in the large n limit. Instead, we could disentangle k of the n qubits, where we keep k fixed as n goes to infinity. This gives a state of the type 2-1 algebra. For finite n, the entropy is n minus k. The way entropy for type 2-1 algebra is defined is by subtracting n before taking the large n limit. So by that definition, the maximally mixed state has entropy 0, and the state with k qubits disentangled has entropy minus k. So entropies are finite, but we achieve that by making a subtraction, by subtracting what was naturally a divergent contribution to the entropy. Now, here I gave one explanation of why the entropy of the maximum mixed state is defined to be 0. It was naturally plus infinity, and we just subtracted away and called 0. But the reason 0 is the natural value is the following. We defined the trace by this formula. Where psi was the maximally mixed state. So the maximally mixed state has density matrix 1. You see, we defined the trace by this formula. So to interpret that as trace of A times rho, we have to say that rho is 1. So we learned that the density matrix of the maximally mixed state is 1. That would not be true with the conventions of usual quantum mechanics. In usual quantum mechanics, the density matrix of the maximally mixed state is a multiple of 1, but it's not actually equal to 1. But for type 2-1, the trace was defined in such a way that the trace of the identity is 1. Therefore, the max rho equals 1 is consistent with trace of rho being 1. So 1 is an example of a density matrix, and 1 is actually the density matrix of the maximally mixed state. Now, if you take the state with density matrix 1 and just formally calculate S of rho, it's minus the trace of 1 log 1, And that's 0 because the logarithm of 1 is 0. So the formal definition naturally gives 0 for the entropy of the maximum mixed state. And it's not hard to prove that any other density matrix has strictly negative entropy. And for example, the state obtained by disentangling k qubits has entropy minus k by the Trace-Rho-Log-Rho definition, just as it does according to this more heuristic discussion here. Now, as I've already explained, in ordinary quantum field theory, the algebras of regions are of type 3. But it turns out, at least for the black hole in de Sitter space, that when we include gravity, even semi-classically, which means thinking of the coupling as being arbitrarily weak, things are different. Gravitational effects, no matter how weak the coupling is, convert the type 3 algebras into type 2 algebras. That can be viewed as an abstract explanation of why entropy is better defined in the presence of gravity. For a type 3 algebra, there would be no notion of gravity, of entropy. For a type 2 algebra, there is. Gravity turns the type 3 algebra into a type 2 algebra, so it brings us to a situation where entropy is a meaningful notion. The details are somewhat different in the two cases, the de Sitter space and the black hole. And today I'm going to mostly explain de Sitter space, although I will briefly explain how to give a similar presentation for the black hole. So here's the setup for de Sitter space. What I've sketched is what's called the Penrose diagram of de Sitter space. So the far future, I guess sometimes called scry plus, is up at the top. Scry minus, the far past, is at the bottom. Then I've considered the world line of an observer. In de Sitter space, the horizon is an observer-dependent notion. So to discuss horizons and entropies, we have to pick an observer. So I've picked an observer whose world line I've chosen to be the geodesic. And it's possible to pick coordinates so that the geodesic is the left boundary of the Penrose diagram. So I've done that. So the vertical line on the left is the world line of an observer who's traveling on a geodesic. The observer starts down here at scry minus, ends up here at scry plus. The green region, well, the diagonal red lines are the future and past horizons of the observer. The observer can't see anything that's past this future horizon. And the observer also can't influence anything that's to the past of the past horizon. So for this particular observer, the one on the left boundary, for that observer, these diagonal lines are the past and future horizons. The region that the observer can both see and influence has been sketched in green, and it's called a static patch. It's called a static patch because it has a time translation symmetry that I will use in a little while. But I guess I'm mentioning it now. There's a killing vector field of de Sitter space of time translations that maps the observer world line to itself, but moves the observer forward in time. So this time translation killing vector field moves the observer forwards in time, and it generates time translations. It's a time-like, future directed time-like throughout the green region. It's actually past directed time-like over here. And it's space-like in these other regions. But importantly, it's future directed time-like in the static patch, and it's past directed time-like in the opposite static patch, the one that's space-like separated from the green patch. Let H be the generator of these time translations. So H is associated to this killing vector field that moves the observer forward in time. In ordinary quantum field theory in de Sitter space, also in the presence of semi-classical gravity, there's a natural de Sitter state that I'll call psi ds, which can be obtained by analytic continuation from Euclidean signature. Correlation functions in this state have a thermal interpretation of the de Sitter temperature, 1 over beta ds, where beta ds is 2 pi times rds. Rds is the de Sitter radius. A slightly abstract way to describe this thermal interpretation is to say that the modular Hamiltonian of the state psi ds relative to the algebra of the static patch. I should have explained that better. We consider the algebra of operators in the static patch. And the modular Hamiltonian of that algebra for this state is a multiple of this killing vector field H. Or more exactly, it's a multiple of the conserved charge H associated to that killing vector field. So the modular Hamiltonian is actually beta times H. Now, in ordinary quantum field theory, we would associate to the static patch a type 3 algebra of observables. In ordinary quantum field theory, we associate to any region in any spacetime a type 3 algebra, and the static patch in de Sitter space is no exception. Including weakly coupled gravitational fluctuations does not qualitatively change the picture. We just include weakly coupled gravitational disturbances along with particles of other types. What does really change the picture is that in a closed universe such as de Sitter space, and de Sitter space is a closed universe because the spatial sections are compact, they're spheres. In a closed universe, the isometries have to be treated as constraints. That qualitatively changes the picture. Although there are other isometries, the important one is this time translation symmetry of the static patch. So to keep the lecture simple, that's the only constraint I'll discuss. This constraint means we should replace the algebra A0 of operators in the static patch by A0H, its invariant sub-algebra. But that does not work. The invariant sub-algebra is trivial. Basically, anything that commutes with the Hamiltonian, or the time translation generator, can be averaged over all the thermal fluctuations and replaced by its thermal average, which is a C number. So the only operators that commute with H are C numbers. So in a second, I'll explain what to do about it, but I think I'll stop here for questions again. To get a reasonable algebra of observables, we include an observer in the analysis. Of course, in principle, an observer should really be described by the theory, not injected from outside. What it really means to include an observer is that we consider what you could call a code subspace of states in which an observer is present in the static patch. So we have a theory that can describe observers. Otherwise, what are we discussing? Well, when we discuss the possible observations in the static patch, that makes more sense physically if there is an observer in the static patch who's making those observations. So what I'm telling you is that to get a reasonable answer for the question we're asking of describing the algebra of observables in the static patch, we need to include in the discussion the observer who's making those observations. So we have a theory that can describe observers. It doesn't mean an observer has to be present, but we consider a physical situation where an observer is present. There might be other stuff present as well. And we're going to, we consider a code subspace of states where an observer is present, but we put no other condition except that the state is such that low energy effective field theory makes sense. And then we'll try to describe an algebra of observables under those conditions. So we'll consider operators that can be defined in the presence of an observer, though they're not well defined in the whole Hilbert space. Now, we could consider an elaborate model, a realistic model of an observer, but it's not necessary. The part that's important is only that the observer has a clock. Well, the observer has a Hamiltonian, and the Hamiltonian of the observer is what I call Q, the energy of the clock. It's physically reasonable to assume the observer's energy is bounded below by zero, so we'll assume that Q is non-negative. You might want to say that the observer's Hamiltonian is bounded below by the rest mass of the observer, so you might want to replace zero with a positive lower bound. It wouldn't be important for what I'll say. The formulas are most elegant if the lower bound is zero, but it's more physical to have a positive lower bound. The effect of including the observer is to modify the Hilbert space from whatever it was before to whatever it was, tensored with a Hilbert space that describes all the states of the clock. So the clock has a Hamiltonian Q that acts by multiplication on functions of Q. So L2 of R plus is the space of L2 functions on the positive half line of non-negative Q. So Q acts as an operator on that space by multiplication. So we slightly enlarge the Hilbert space from H0 to H0 tensor L2 of R plus. I'm going to assume the observer can manipulate the clock in an arbitrary fashion. So the algebra then is extended from A0, the naive algebra of low energy effective field theory in the static patch, to A0 tensored with the type 1 algebra B of L2 of R plus of all bounded operators in L2 of R plus. So it's generated by P and Q. Finally, the constraint becomes the total Hamiltonian of the quantum fields plus the observer. So instead of imposing as a constraint the killing vector field associated with time translations, we should consider the killing vector field of time translations plus the Hamiltonian of the observer. And that's the combined constraint H hat. So the correct algebra of observables, taking account of the presence of the observer, is obtained by two changes from what we had before. We replace A0 by A1, and we replace H by H hat. So the correct algebra of observables is the H hat invariant part of A1, and not the naive answer. Remember, the naive answer was the H invariant part of A0. This is the wrong answer. That's over here is the right answer, taking into account the presence of the observer. Well, why does it help us to include the observer? Once an observer is present, we can gravitationally address any operator to the observer's world line. So for any A of the naive algebra, we define the operator A hat, which is e to the IPH times A times e to the minus IPH. And a short calculation will show you that that gravitational address operator commutes with the constraint. So in the naive approach, we didn't have any operators that commute with the constraint. But in the improved approach with the observer, we have a lot of operators that commute with the constraint, namely gravitationally addressed versions of all the operators we would have had without gravity. There's one more operator that commutes with the constraint, namely Q itself, or equivalently minus H. The reason it's equivalent to, say, Q or minus H is that the difference between them is H hat. H hat is a constraint, so it annihilates all physical states and commutes with all physical operators. So H hat is effectively zero, and therefore it doesn't matter whether we say that the extra operator is Q or minus H. Now, if you look for more operators that commute with the constraint, you'll convince yourself after a little while that there aren't any more. If you want to know who proved that, the answer is that, well, there are classic results of Kahn and Takasaki from the early 70s, which by coincidence were proved at almost the same time that black hole thermodynamics was getting started. That assert the The following two statements are an important part of the work of Kahn and Takasaki. First, there are no more operators that commute with the constraint. And secondly, the algebra curly A that's generated by the operators that commute with the constraint is of type 2. And since it's of type 2, we're going to be in a world where entropy is meaningful. To be more precise, the algebra A that we get this way is type 2 infinity if we do not stipulate that the observer energy Q is bounded while. If we do impose this condition, the algebra turns out to be of type 2-1. Of course, it's physically natural to say that the observer energy is bounded while. And to get a model of de Sitter space, we had better get an algebra of type 2-1, because it's believed that in de Sitter space, I should have explained this before, there is a state of maximal entropy, namely empty de Sitter space. Oh, sorry. This sentence is what I just told you. It's believed that de Sitter space in the presence of gravity has a state of maximum entropy, namely the state psi ds that's defined by analytic continuation from Euclidean signature and represents empty de Sitter space. It really represents quantum fluctuations around empty de Sitter space. But it's believed that this state is the that in de Sitter space, this is the state of maximum entropy. So in particular, for a good algebra of observables in de Sitter space should be such that there is a state of maximum entropy. And to make that happen with the construction I'm telling you, we need the observer energy to be bounded below so that the algebra comes out to be of type 2-1. So we can really only get a model of de Sitter space if we assume the observer energy is bounded below, which you might have thought was a natural assumption anyway. Once we get a type 2-1 algebra, there's going to be a state of maximum entropy with density matrix 1. It's not difficult to identify this state. And if you look at the paper, I'm going to have to, in the remaining part of my talk, give less thorough explanations because of the time. But I'll be telling you things where you'll find quite thorough explanations in the paper that I mentioned at the beginning.
I have a question here.
Yes,
So you talk about in the de Sitter space, you mentioned that this density matrix is identity. Does it consistent with this temperature? You also talk about the temperature of the de Sitter, right?
That's a very good question. And you're the first who's asked when I've given this talk. I'll answer it in about 7 minutes, I think. So, okay. To explain the question for everyone, the questioner is pointing out an apparent contradiction. A state of maximum entropy normally corresponds to infinite temperature, where everything is maximally mixed.
Yes.
But it's claimed that de Sitter space has thermal properties at the de Sitter temperature. So how are we going to reconcile those claims? I'll reconcile them as a guess in about 7 minutes. I see I'm running out of time, but in fairness, we've had a few questions. It's not difficult to identify the state of maximum entropy, but you'll have to look at the paper if you want to see the details. The maximum entropy state is the state that would describe empty de Sitter space if there was no observer, tensored with a thermal state of the observer at the de Sitter temperature. And you could show that that's the state whose density matrix is 1. It's not a very surprising answer because you'd guess that since the density, well, if we're trying to discuss a state that's thermal at the de Sitter temperature, to get something simple, we should put the observer in thermal equilibrium at that temperature. And it turns out if you do that, you get the state of maximum entropy. So we can draw a few easy conclusions which harmonize with claims made previously by other authors, though I won't have time to explain their ideas. And after drawing a few easy conclusions, I will then answer the last question about why. Well, we'll get back to the question in a moment, and then we'll answer it. First of all, since the maximum entropy state is 1, its eigenvalues are all equal, namely they're all 1. It has a flat entanglement spectrum, which is jargon for saying that the eigenvalues of the density matrix are equal, and accordingly its Raney entropies are constant, they're all 0. Rho is 1, so 1 to the alpha is 1, trace of 1 to the alpha is 1, and the logarithm of 1 is 0. So the Raney entropies are all 0. Given the assertion that de Sitter space has a state of maximum entropy, you should expect that the state of maximum entropy has a flat entanglement spectrum. That's what happens in ordinary quantum mechanics. In ordinary quantum mechanics, the maximum entropy state is maximally mixed. Its density matrix is a multiple of the identity, so the eigenvalues are all equal, and the Raney entropies are independent of alpha. So what we found is exactly analogous to what would happen for a maximum entropy state in ordinary quantum mechanics. On the other hand, suppose the observer makes a measurement with two outcomes that correspond to projection operators pi and 1 minus pi. The probabilities of the two outcomes are trace of pi and trace of 1 minus pi. And Murray and von Neumann showed that for suitable choices of pi, any value of trace pi between 0 and 1 is possible. If the outcome corresponding to pi is observed, then after this measurement of the density matrix is what I've drawn here, it's pi, except for a normalization factor to make trace sigma equal to 1. And now we can compute the entropy. Since the two eigenvalues of sigma are 0 and 1 over trace pi, you see that sigma log sigma is the same as sigma log 1 over trace pi, because whenever sigma isn't 0, it's equal to 1 over trace pi. So if sigma is 0, it doesn't matter what the log is, and if sigma is 1 over trace pi, then the log is the log of 1 over trace pi. So the entropy after the observation is minus trace sigma log sigma, which evaluates to minus log of 1 over trace pi. But you see the probability of the outcome corresponding to pi was trace pi. And if you do get that outcome, you reduce the entropy by this amount. Well, you reduce the entropy by the log of, the entropy is reduced by the log of 1 over trace pi. So you see the probability of an outcome is related to the entropy reduction by p equals e to the minus delta s. Now that's what you'd have in, however, as was remarked in the last question, it's believed also that de Sitter space has a thermal interpretation. And that would tell us that the probability of an energy E fluctuation of the static patch should be e to the minus beta ds times E. So we have two different formulas for the probability of a given fluctuation. It should be this, but it also should be this, or this, e to the minus delta s. So for consistency of the two descriptions, it must be that e to the minus delta s is the same as e to the minus beta ds times E. In other words, thermal fluctuation of thermal suppression by this factor can be understood as purely entropic suppression by this factor. Now, with the type 2 algebra, I'm giving a general explanation that this should be true for all states, but it was discovered originally by considering a special case. If the fluctuation is a small black hole at the center of the static patch, then for E, you use the mass of the small black hole, but for delta S, you use the reduction of the horizon area. So when you add a black hole in the static patch, it causes the cosmological horizon to be smaller, and the sum of the two horizon areas is less than the original horizon area of empty de Sitter space by just an amount delta S that makes this true. That was, well, I mentioned earlier, that was described in most detail by Susskind, but related ideas have been developed by Banks and others that I mentioned before. So which part of this is surprising? Well, the formula e to the minus delta s for the probability of an outcome is really an inevitable consequence of having a maximum entropy state. A maximum entropy state is one in which all states are equally probable. In other words, if all states are equally likely, the probability of a given outcome is just proportional to the number of microstates that are compatible with that outcome. Here I'm using language appropriate for ordinary quantum mechanics with a finite dimensional Hilbert space. I already earlier explained how the more abstract derivation of that conclusion in the context of the type 2-1 algebra. But the conclusion we reached would have held in ordinary quantum mechanics whenever you have a maximum entropy state. The surprise is not that the probability is e to the minus delta s, which we should expect for a maximum entropy state. The surprise is that the maximum entropy state also has a thermal interpretation. So let me discuss how to see this in the context of the type 2-1 algebra. And here's where I'll answer that last question. First of all, ignoring the constraint for a moment, the time dependence of an operator in the naive quantum field theory algebra A0 is given by conjugating with the Hamiltonian. So what we usually call A of t, the operator at time t, it's obtained by conjugating the original operator by e to the IHT. Then time-dependent correlators such as this one, in the case of the empty de Sitter space, have thermal properties that reflect the fact that these correlation functions can be computed by analytic continuation from Euclidean signature. After imposing the constraints, we don't have the operator A, but it has a dressed version A hat. And again, we define its time dependence by conjugating by the Hamiltonian. Then, because the Hamiltonian, remember H is the two-sided Hamiltonian, the conserved quantity, H is a constraint operator, so it annihilates the thermal state. And using this fact, we rather trivially find that the expectation value in the maximum entropy state of the type 2 algebra of gravitationally dressed operators is the same that you'd have without gravity with the naive operators. So therefore, the correlators of gravitationally dressed operators, after imposing the constraints, have the same thermal properties that the correlators of bare operators had before imposing the constraints. So weakly coupled gravity does not disturb the thermal interpretation of de Sitter space, but it leads to a new interpretation that we would not have without gravity. The natural de Sitter state is a maximally mixed state of maximum possible entropy. Now, I'd hope to explain a few more things, but I'm actually out of time. So I kind of have to ask the organizers what they want me to do. We could stop here. Yes.
Okay. Thank you, Edward Witten, for a very interesting talk.
Well, thank you.
Okay. We have 30-minute break after the session. So if it's okay, you can go on and you can use time more and flexibly.
Okay. I'm not sure how much I should do. So let me try to finish in about 10 minutes. Is that okay?
Okay.
Yeah, I hope I can do that. So before comparing to the case of a black hole, I want to explain the answer for de Sitter space slightly differently. So we have the algebra A of gravitationally dressed operators along with the observer Hamiltonian Q. But before comparing it to the black hole, it's useful to conjugate by e to the minus IPH. And if you do that, you'd say that the algebra is generated by the naive operators and Q minus H. So from that point of view, to include the observer and the constraint, we do two things. One is we slightly enlarge the Hilbert space by including a factor of L2 of R plus. And secondly, we keep all the old operators and we add one more operator, Q, H minus Q. So that's not the way I described it in the main part of the lecture, but this is an equivalent description of what was the answer for de Sitter space. I've explained it this way because the answer for the black hole is more easy to understand in this language. So now we're going to consider a black hole, say, in an asymptotically flat spacetime. So I've drawn a two-sided, maximally extended black hole, and A and B I take to be the regions to the right and to the left of the horizon. So there are two asymptotically flat regions. We live in one region, we make observations here. We want to define an entropy for the algebra of observables in our universe. We don't really know what there is behind the horizon, so we don't really know if there's really a second region with somebody else doing the same thing. We want to construct an algebra curly of observables for an observer in region A. In ordinary quantum field theory, we would construct a Hilbert space H0 of quantum fields in this space-time. We do it, do I show it? No, okay. We do it, we take an initial value surface, it could be that one, for example. Then we would take the fields on the initial value surface and quantize them, and we'd get a Hilbert space. And that would be H0. It would be a two-sided Hilbert space. It would describe fluctuations on both sides of the horizon. Then in ordinary quantum field theory, we would have a type 3 algebra A0 of operators in region A, this region, so this region here, acting on the naive Hilbert space. Adding small gravitational fluctuations that can be observed locally does not qualitatively change the picture. The Hilbert space H0 and the algebra A0 become bigger, but the algebra is still of type 3. What does qualitatively change the picture is that there's a mode, the relative time shift between the two sides, that cannot be measured locally. If you make, you could make a time translation, you could make a diffeomorphism that's nothing on the left. Sorry. You make a diffeomorphism that's nothing here. Then you move forward in time here. And as you go from the right to the left, you make a more general diffeomorphism. It's not a killing vector field. That does less and less the more you move to the left. So this diffeomorphism creates a new spacetime that's actually diffeomorphic to the old one, but not by diffeomorphism that's trivial at infinity. So it's actually a physical mode. It's a shift in the zero of time between one side and the other. For example, when Lenny Susskind claims that the volume of the maximal slice is the complexity of the quantum state, he's studying the complexity of the state as a function of this relative time shift. Anyway, I don't know if my explanation was adequate, but it's all I can do in the available time. But in gravity, there's one mode, a relative time shift, that can't be measured locally. So the Hilbert space is not H0. It's H0 tensored with L2 of R, where L2 of R consists of functions of the relative time shift. There's also one extra operator that can be measured in the presence of gravity and does not have an analog in ordinary quantum field theory. That's simply the ADM energy measured at infinity. To explain why it's important, let's discuss the bulk picture. Here's the bulk picture. There's a killing vector field of time translations. As in de Sitter space, the time translations move forward on the right and backward on the left. There's a conserved charge H that generates these time translations. In ordinary quantum field theory, there's no formula that says that H is an operator on the right minus an operator on the left. If you try to find such a formula in ordinary quantum field theory, you'll find that H right and H left are affected by ultraviolet divergences and don't exist, only H does. But in the presence of gravity, with H right and H left understood as the ADM Hamiltonians defined at infinity, we do have H equals H right minus H left. Moreover, H right is an observable for an observer at infinity in region A. Denoting H left as X, that means that the algebra A of observables in the region A to the right of the horizon is generated by the naive algebra A0 and one more generator, H right, which is rewriting this formula. It's the same as H plus H left, or in other words, it's the same as H plus X. So coupling to gravity modifies the answer we would have for the observables outside the horizon in ordinary quantum field theory by doing two things. We slightly enlarge the Hilbert space, and we add one more generator. That's the same as we had in de Sitter space if we identify Q with minus X. And also, we have to remember that in de Sitter space, we took Q to be bounded below, but that has no analog for the black hole. So we've gotten almost the same thing as in de Sitter space without this lower bound on the energy. So it turns out that this means that the algebra is of type 2 infinity rather than type 2-1.
And why the black hole does not have the analog, the bound?
Well, it doesn't have an upper bound on the energy because its energy can go up to infinity. And it doesn't effectively have a lower bound because we took G to 0. We're working near G equals 0, keeping fixed the size of the black hole, although I didn't stress that. So the black hole is extremely massive. In the small G limit, the black hole entropy, mass, it's proportional to 1 over G, so it's very, very large. And there's no upper bound on how much you can reduce the black hole mass. So you can increase or reduce the black hole mass by any desired amount. And therefore, there's no upper or lower bound on Q in the case of the black hole.
I see. Okay. Thank you.
Okay, sure. Now, I really don't have time, and I apologize for running over. I just want to say, I don't want to explain this in detail, but I'll just tell you that to prove that the algebras are type 2, you want to know that there's a trace, and there's a concrete formula for the trace. I won't go through it, but anyway, the proof is in my paper from December. So the formulas in my slide do not represent a proof. All I did in the slide is to write a formula for the trace, just to make you comfortable that when I say that it's a type 2 algebra, very concretely, it has a trace we can describe explicitly, so we know it's a type 2 algebra. And if you are interested in how to prove that this function is a trace, you can look at the paper from December, although I'm explaining results that are originally due to people like Kahn and Takasaki. Then you'll find that for the black hole, the integral that you need to define the trace doesn't always converge. So the trace is not defined for all elements of the algebra. That's the right answer in a type 2 infinity algebra. But for de Sitter space, the constraint that Q is non-negative or X is non-positive cuts off the dangerous region of the integral. And now the integral always converges, and you get a type 2-1 algebra. So in sum, I've given a somewhat abstract explanation of why, at least for de Sitter space and the black hole, the existence of gravity makes entropy better defined than it would be in ordinary quantum field theory. Now, there's something that should bother you. I'm not going to have time to explain the answer, but I just want to tell you that there is an answer and what the question is. Does entropy defined this way agree with entropy defined by more familiar field theory methods? That's not obvious from anything I've told you. And if it's not true, then what I've told you would not be interesting. Well, we can only expect this to work for states where the right-hand side is well-defined. That means semi-classical states. And if you look at, I think, section 3 of the paper with Chandrasekhar and the others, we explain how to show this formula, how to show that the entropy of a state of the type 2 algebra agrees with the generalized entropy up to an additive constant that's independent of the state. That additive constant is unavoidable because in defining entropy for the type 2 algebra, we subtracted a divergent constant. So I really will stop here, and I do apologize for running over. Thank you for your patience.
Thanks, speaker, for the interesting talk. Does anyone have a question?
May I have a question?
Please.
Thank you. I'm Koji from Kyoto. So I'd like to know more about the last page of your slide. Yeah, I was wondering how this semi-classical statement can be connected to your restriction to sub-algebra, which is invariant sub-algebra. So naively, I expect that
How could I restrict to a sub-algebra?
So you went to this invariant sub-algebra to define entropy, right?
Well, making the sub-algebra invariant means imposing the gravitational constraints. So the invariant sub-algebra is the correct algebra once you include gravity.
Yes, I understand that point, but generically, this divergence coming from the renormalization of gravitational constant depends on what kind of gravity theory you have, right?
Well, we've already made the renormalization. When we defined the type 2 algebra, we did renormalize the entropy.
Sure. But actually, does it actually agree with the normal divergences which we expect in quantum field theory of gravity?
Well, I would prefer to say that we compare the physical quantities, not the divergences. So they both have divergences. You know, in general, in physics, the divergences, what you say about the divergences can depend on your formalism. But usually you say that the physical answers agree. So the entropy of the type 2 algebra is more general than the generalized entropy defined by this formula. This formula is for semi-classical spacetimes. So compared to it, we had to specialize the type 2 algebra to semi-classical states. A semi-classical state is a state that can be described to good approximation by specifying the state of quantum fields in a definite spacetime. So in semi-classical states, we were able to show that the entropy of the type 2 algebra agrees with what a field theorist would have.
So does it mean that we have to restrict possible gravitational theories so that the entropy formula actually matches yours?
Sorry. Well, we used Ehrenmoll's formula for the generalized entropy in terms of a relative entropy along the horizon and also the area at future infinity.
Yes.
So in any theory of gravity that has a formula similar to that one, we'd be able to compare to it.
But the divergent part, which comes from the renormalization of gravitational constant, actually depends on what kind of gravitational theory you have, right? For example, if you have higher derivative terms, then...
Well, I'm not sure that there are other non-perturbative other theories where the discussion makes sense. You see, we put this in the context of Aaron's proof of the generalized second law. Is there a generalized second law for the other theories? I personally suspect the other theories only exist in a perturbative sense. However, I think this is not really the right answer to your question. I think the right answer to your question is that we only compared physical observables. And even for the physical observables, our comparison has an arbitrary constant. So in other words, in the type 2-1 algebra, the entropy of empty de Sitter space is defined to be 0. Whereas Beckinson and Hawking would say, Gibbons and Hawking would say that the entropy of empty de Sitter space is the horizon area over 4G. So of course that goes to infinity as G goes to 0. And our discussion is an expansion around G equals 0. Anyway, we can't see the part that's divergent as G goes to 0. So the constant that we subtracted is the entropy of empty de Sitter space. That's the piece we don't see. We do show that entropy differences agree with the standard discussion when the standard discussion is well defined, which means for semi-classical situations.
Yes. Okay, thank you very much. I think I need to think more about that. Thank you very much.
Sure, but I'll be happy to discuss it further offline if you have any more questions.
Thank you.
Any other questions?
I'd like to have one question.
Yes.
Do you have some more physical picture for the gravitationally dressing?
Well,
for example,
sort of.
Think about it.
So, okay, I just told you that this was gravitational dressing.
Yes.
And the reason I told you was just that A hat commutes with H plus Q. Now, since Q was the observed Hamiltonian of the clock, you can argue that P is the time told by the clock. So we've advanced the operator in time by an amount defined by the observer's clock.
And why did you call it as a gravitational dressing?
Well, the gravitational Hamiltonian, the H which appears here is the gravitational constraint operator. So we definitely use gravity. But you see,
but it is not, I think, that maybe related to any of the equivalence principle or.
Well, it's an abstract version of gravitational dressing. What would other people say about gravitational dressing? So this is meant to be the Penrose diagram. Here's the observer world line. Here's an operator you want to dress. Well, the trouble with, well, let me describe it informally. You can't impose the constraint. The trouble with the operator, let's say, lives here, but you can't impose the constraint naively because it would move the operator along the time translation orbits. And to make the operator time translation invariant, you'd have to average it over the orbit. And then it would become a C number because you'd be averaging over all the thermal fluctuations. But what gravitational dressing means is that once you have an observer, since the constraint would also change the time told by the observer's clock, you can say, I want to define this operator when the observer's clock tells time 0. So what some people would do is to try to drop a geodesic from the operator to the observer's world line, and then use a gravitational Wilson line. But there are different ways you could do it, but once you have an observer in the discussion, you can define operators that commute with the constraint. This is the most efficient way to do it. You might prefer other ways at first, but I think you will eventually get used to this. It's hard for me to give a better answer, I'm afraid.
Thank you for your answer.
Sure. Are there any more questions?
Oh, yeah, I think. Okay. There is a question in offline.
Where's the question?
It is my, yeah. So I have a question. So
Yes,
in Minkowski space, one can consider the Lindora horizon in Lindora coordinates. So can we construct type 2 algebra by using Lindora horizon instead of black hole horizon or Rosetta horizon?
In Minkowski space?
So can we can you construct a type 2 algebra by using Lindora horizon instead of black hole horizon or
You want like the horizon of an accelerated observer? Is that what you're asking? I'm not sure I understand.
Oh.
I'm missing a word. What horizon you're interested in? I missed one word.
So my question is about Lindora horizon, Lindora coordinates in. So I So my question is about Lindora horizon in Lindora coordinates.
Coordinates
So,
in Minkowski space. Yes.
so I think you discussed about type 2 algebra by using Dojita horizon or black hole horizon.
I use the observer horizon. Well, I don't know the answer, but I think it's reasonable. Take it. Hawking said that an observer who doesn't see the whole universe doesn't have pure states, but has to describe quantum mechanics by density matrices.
Mm-hmm.
However, if the algebra accessible to the observer is of type 3, technically Hawking's statement isn't correct, although you might think it's correct in spirit. If you want to make Hawking's statement literally true, the algebra accessible to the observer has to be of type 2.
Mm-hmm.
I don't know whether that's always true, but it would be really nice if it is always true. So that's the most general result I would hope for, but I have no idea if it's true. To recapitulate, the most general result I would hope for is that for any observer who does not see, who has cosmological horizons, let's say past and future cosmological horizons, for any such observer, it would be nice if the observations accessible to that observer are always of type 2. I don't know if that's the case. Sorry, type 2 or type 1. An observer at rest in Minkowski space would have a type 1 algebra.
Mm-hmm. Thank you.
Sure, but I think I didn't answer the question because I unfortunately missed one word. Are there any other questions?
Are there any questions from audience? So, if not, I think this may be a good time to close this session. And thank you very much, Tin.
Oh, well, thank you. And thank you for all the discussion and questions.